This video is intended to be a recap of our constant velocity post-lab discussion. So let's get to it. Let's start by talking about what we actually did in the lab. We started with a discussion about independent and dependent variables and how to go about collecting the data so that we could determine if the car was moving at a constant rate. So to do that, we had two possible scenarios or ways to collect data, and we settled on the one where time, measured in seconds, is the independent variable, and position, measured in meters, is the dependent variable. How did we do this? We started by setting up an origin, a frame of reference, sort of like a number line. Everyone had a 0 starting point, and we had established a positive and negative direction. After that, we started the car and the stopwatch at the same time after placing the car at the appropriate starting point. And then to keep this short and sweet, we simply placed a paper clip at the location of the car, or the position of the car, every set amount of time. Let's just call it every 3 seconds for the sake of this discussion. So every 3 seconds, someone on your team, in your lab group, said now. You placed the paper clip at the location of the car and marked its position. So you sort of ended up with something that, as your car moved along the number line, may have looked something like this. Okay, so you can see how the paper clips marked the position of the car as the car moved forward in time. So that's kind of the basic idea of what we did. So then once we had the data, we took the data, and your assignment was to make a graph. So we graphed position versus time. Again, position is on what from math class is called the y-axis, the dependent axis, and time is on the x-axis, which is the independent axis. And when we made our graphs, everybody came up with a graph that looked something like one of these. So we had situations that looked like this, situations that looked like this. We had situations that may have looked like this guy, or this one here, or starting at the origin and moving in the negative direction. So you had a graph that essentially was a straight line, straight best fit line. Your points may not have fallen exactly on the line. For example, points on this for this best fit line may have looked something like that. But the general idea is that these were linear. All of these curves are linear. These best fit lines are simply linear lines. And that was important because what we want to do, or one of the things that we want to do, is be able to mathematically model the motion of the object. So what we did is we took our graphs and we had to come up with an equation. Now, of course, you had values for some of this stuff. For example, you had a value for what this location was, what your starting position was, and you had a value. You were actually able to calculate a slope for your line because you had data points to work with. But without having the data points here, we can still talk about it in the general. So let's look at the general case where maybe your graph looked like this. And what we want to do is we want to take our best fit line and come up with the equation. So let's start with the math class version of the equation. So in math class, since this is linear, we would say that this thing has an equation of y equals mx plus b. And if we look at this from the standpoint of your data, you may have then come up with something that sounds like y equals 0.25 x, whoops, let's make that look more like an x plus, let's just use 1 for now. So this could have been the equation that you came up with. And I'm generally okay with this equation, except for the fact that I want the equation to reflect the physics that we're talking about, the actual physical variables that are involved. So we're going to make some changes, and I also want to come up with the general case. So one of the things that we did is I asked you to let me know what the units are for these numbers. And the units for the slope, since our x-axis is measured in meters and our t-axis is measured in seconds, your slope has units of meters per second. And it turns out then that the y-intercept of this graph has units of meters. And these units can help us figure out what these values actually are. The other thing that I want to do is I want to change the variables, because in physics, in this particular case for physics, y and x are not appropriate variables. I want variables in here that reflect the quantities that I'm talking about. So for physics class, I want to reflect the physical variables that we're talking about. So instead of y, our y-axis being this vertical axis over here, we actually have x as a variable. So I'm going to go ahead and replace that with x. And in class we actually made this a little bit more specific by discussing that this variable here, x, is really it's a function in time. So what we're actually talking about with this x is we're actually talking about x of t. We're actually talking about the position at any particular time, which is going to make sense even more when we rewrite this as x equals 0.25 and we use t instead of x. You can see that the x value will change as you plug in different t values, and plus 1. But I want to make sure that that x is more specific, so I'm going to put a little f there. And the reason I'm going to choose f is f stands for final, your final position at the end of this particular time interval that we're talking about. We're making the assumption that we're starting time at 0. So we're kind of looking at it as, okay, at the end of 3 seconds, for example, if we were to plug 3 in for t, our position at the end of that 3-second time interval would be this value xf. So this is more of the physics equation that I want to have you be able to come up with from one of these graphs that we make of our data. In addition to that, we also need to be able to take these equations and make them more general. So what is it that we're talking about? So it's kind of easy to start this one off because xf is already here for us. So we're going to start with xf, and we're going to say xf equals, now what is 0.25? So one of the things that is very helpful in determining the meaning of a number in our equations are the units. So if we look here at this meters per second, we can start to figure out what does that mean? 0.25 meters per second. So in a previous video we talked about what the slope means and how to discuss that, and so we can restate this or rewrite it actually as 0.25 meters per second, and we can look at this as 0.25 over 1. So this says that for every 1 second that I allow the car to drive, to keep moving, it will change its position by 0.25 meters. And if we also look at this as, well, meters is a unit of measure of distance, and seconds is a unit of measure of time, we can kind of relate this to speed a little bit, and we can talk about this as miles per hour. Meters per second and miles per hour are similar units in that it's a distance over a time. And so what we talked about in class is that this 0.25 is actually the velocity of the object v. And we talked about it being a velocity as opposed to a speed because our slopes on our graphs could be negative, and therefore they have a direction, the positive direction and the negative direction, which makes them a vector, and that makes the velocity just a little bit different than speed. So we're going to go ahead and we're going to use v velocity here because the sign of that slope is going to be very important for us. Keeping up with our equation, we can move forward and we can bring that t down, and we can say, okay, xf equals v times t. And that should kind of be familiar because that kind of looks like distance equals a rate times time that perhaps you've seen in math class. And then the plus 1, we can write this as plus, well, what is that 1? That 1 is 1 meter, and that 1 meter is actually this spot on the graph right here. From math class, it's the y-intercept, and here it would be our position intercept, or our x-intercept. And in this case, what we're looking at is we're looking at the position that you were at when time was 0. So that would be the position that you are in when time starts, or initially, and that's why we call this the xi, or xo, sometimes you might see x naught, and that means it's the initial position, it's the starting position, it's the position that you are in at the beginning of time. And so this is a general equation that we're going to use and see quite often as we move forward here, that xf equals vt plus xi, and we can rearrange this equation. Rearranging this equation and solving it for v actually gets you the definition for average velocity. I would like to show that really quick right up here. So we're going to start with xf equals vt plus xi. If we move xi to the left by subtracting on both sides, minus xi, we get xf minus xi equals vt. And again, to solve for v, I would divide by t, but I do want to point out that xf minus xi is something important, and xf minus xi was the equation that we had for delta x, or the displacement. And so what we actually see when we finish this out and substitute delta x in is that the average velocity is equal to delta x, the displacement, divided by time. How much did you change your position, and how much time did it take? And that's gonna equal the average velocity. And so that kind of brings in the delta x portion. If we were to consider speed, speed would be equal to distance divided by time. And so one of the things we talked about in class is that distance is not a vector, and therefore speed is not a vector. Speed doesn't have a direction. 45 miles per hour that way down the road, and 45 miles per hour this way down the road are just 45 miles per hour. Those are speeds. When you actually take into account something like 45 miles per hour north versus 45 miles per hour south, we're adding that direction in, and that direction becomes important. And in physics, we don't like to use north and south. We like that positive, negative, that more mathematical feel to it. So kind of a lot here, but this equation and this equation down here are going to be two important equations for us moving forward. Okay, so the graph kind of gets us a good start, and it gets us to the point where now we can do some more things. And so the first thing that we've done here is we've talked about using the graph, one representation of the motion, to create a mathematical model, also known as an equation for the motion. But these aren't the only representations that we're going to see or be responsible for. So let's also look at what's called a written description. So let's take, for example, this x versus t graph, which, we can start with this one. You could be given any x versus t graph. You could be given an x versus t graph like this one that's qualitative. You could be given one that's quantitative. But one of the things that you could be asked to do is to write a description of the motion. Now, I want to be careful here because I've run into a lot of situations where students will describe the graph, and I don't want you to describe the graph. The written description is the description of the motion. So what is this object doing? So for example, you don't want to say something like, oh, it's going down because the line is going down. Well, the line is going down, but that's not necessarily what the object is doing. So you have to think about this as, what would your car from the lab have to do in order to make this graph, in order for the data to come out looking like this? And so when I try to focus students on the written description, I try to focus them on three things that they should include. And you need to include this for each section of the graph. And as we move forward and the graphs get more complicated, we start to see that the entire graph, this kind of graph may not be the entire graph. We may change directions and add a section of the graph that looks like this. And so you need to include each of these 3 specific parts for all of the pieces of the graph. I'm going to take that orange line away, though, first. And so the 3 things that I want you to include are the starting position. Okay, I'm going to list that as XI, so we kind of get familiar with that, the initial position. You should talk about the direction. What direction is the object moving? And then finally, you should describe the velocity. And we'll do it here, and we will, get an idea of how to do that better, because we don't have any numbers on this graph, so that's going to kind of complicate things just a little bit. Alright, so when we do this, since starting position is one of the things, it's probably the best place to start. So let's start there. So the object starts at we could describe the starting position in this case as some positive number. It is a positive value. Starting position is up here. It is somewhere up on the graph. Now again, I'm describing the graph now, but where the object would start would be at some positive position. So the object starts at a positive position. Positive position. Okay. And so the next thing that we talked about was the direction. So what direction is this object moving? The line is going down, and the line going down tells me that this object is moving in the negative direction. So let's put a period here and say the object, moves in the negative direction. Sometimes it may be helpful to say something that moves in the negative direction toward the origin, right? Because it is moving back towards the origin, our reference frame. But toward the origin is not always the negative direction, so that's something to be careful with. So for example, I could be, if I'm at a negative initial position and I'm moving toward the origin, I'm going in the positive direction. So we can be careful with that. But that's something that you could include and state that it is moving toward the origin. And then, how do we handle the velocity part? Well, since we don't know what the velocity is, we don't have numbers, we can't actually calculate the slope of the graph. What we can do is we can say that it's constant. We can at least say that since this thing is linear, we know that it is moving at a constant velocity. So it moves in the negative direction at a constant velocity. Okay, so again, we couldn't put a number to it, but what we're able to do is say that at least it's constant. It's linear. This slope does not change, and the slope of a position versus time graph is the velocity. The value of that slope tells me what the velocity is. So if it's constant, I know that the velocity is constant. If it's negative, I know that the velocity is negative and that I'm moving in a negative direction. So for a written description, we can at least make sure that we talk about the initial position, the direction, and the velocity, and we should do that for each section of the graph in case there are multiple sections. Okay, so the next representation of motion that I want to talk about is a V versus T graph. And so sometimes it's helpful to graph and be able to visually look at the data of what the velocity is doing. We know that it's constant, we know that it's not changing, and so it's important that we're able to take that and turn it into a graph that looks appropriate based on the data that we have. And so I want to go to the next screen to try to talk through that a little bit. So for the situation that we have here with the X versus T graph that we're using, this isn't really difficult. What we know is that the slope of an X versus T graph is the velocity. and that's really important. It's also important to note that the y-intercept is the initial position. These are things that you just have to kind of pound into your brain and make sure that you regurgitate on command, because it comes up very often. And the slope of this guy, we just said, is constant, which means it's not going to change, and it's negative. So it should be pretty easy to come up with what this graph should look like. But I want to talk through it because as things get more difficult, it'll be good for us to kind of see how we're doing this and how to make the graph for something that's more complicated. And so what we're going to do is we're going to make time and velocity data and put it in this data table right here so that we can plot it. And so what we're going to do is we're going to look at the velocity, also known as the slope, at different times. So I'm kind of going to pick a time down here and call it t1, and I'm going to look at, hey, what's the slope? If I were to calculate the slope of the line right here, what is it? So at t1, the slope is whatever v is, the velocity. And then I'm going to move over to t2, whatever t2 I decide to use, and I'm going to say, all right, what's the slope right here? All right, and I can pick a point over here and a point over here and calculate the slope using the slope formula, which also happens to be that average velocity formula that we talked about earlier, v equals delta x over t, remembering that delta x is xf minus xi divided by t, and t is kind of tf minus ti, where ti is basically 0. So really calculating the velocity is just calculating the slope. That's all it really is. And we would determine then that the velocity that we get right here happens to be, at t2, the exact same velocity that we get for t1. And if we do it again at t3, since this is constant, guess what? Same velocity, t3, v. Now, all of these v's are negative values. Okay, so let's throw a negative sign in there just to be clear. And then we can say, well, couldn't we just plot these to make the graph? Just like we plotted our position and time data and put a best fit line in, can't we plot our v and t data and then put a best fit line in there? So sure, why not? So let's go to our v versus t graph, v in meters per second and time in seconds, and say, all right, let's go over to t1, and here's negative v, and there's a data point. And if we go to t2, we got another data point right there, and here's t3, there's another data point, and if I put a best fit line in here, I get this nice horizontal line. And the horizontal line is good because it tells me that the velocity is not changing. The velocity is staying at some constant, in this case negative, value, and that's exactly what we talked about that our car in our x versus t graph has. It has a negative constant velocity. So this v versus t graph fits rather nicely, and again, it's something that we could come up with relatively easily just based on the discussion that we had, but I think it's good to understand this idea of collecting the data and using the position versus time graph to help us come up with the v versus t graph. In a qualitative situation like this, you may be expected to be able to go from this graph to this graph without any data. So you do need to be able to be prepared to look at this and say, negative constant velocity. So if you're able to state constant velocity, you should automatically know that this v versus t graph is going to be a horizontal line. Nice and flat, constant, no changing value. So get used to that. So if we come back over here, we can fill in what our v versus t graph looks like. Alright, so we have that filled in now, the v versus t graph, and there is an empty box over here to the right where we are going to talk about another representation of motion in a second, but while we're on the v versus t graph, I think it's a good time to point out another important physical quantity that we can determine using this graph. So not only does it get us give us an idea of what the velocity is doing, what this object is doing as it moves through time, and in this case it's keeping a constant negative velocity. We can also use this to help us figure out something else, another important physical quantity that we've talked about. And when we do that, we like to talk about what's called the area under the curve. Okay, so the area right here. So I'm going to put AUC, the area under the curve. And this is a common math and physics term. This is actually called an integral when you get to calculus. But it turns out that this thing is a rectangle. And so we can easily determine the area of a rectangle, and we do that by calculating base times height. And so in this case, the base is whatever this time is. How long is this side, right? So it's some amount of time, whatever that is. And the height here, base times height, or length times width, whatever you want to go with here, but the height is whatever the velocity is. And in this case, it's negative, which is fine. I know you don't usually have a negative area, but if we remember that the negative sign is giving us information about what's happening, if we calculate this area, we actually see that it's the velocity times the time. And we've actually already seen that equation earlier in this discussion, and so it turns out that this is the displacement. And the displacement in this case would be a negative value, remembering that displacement, delta x, is equal to xf minus xi. Your final x right here is going to be a smaller value than your initial x right here. And so when you subtract those, you do actually get a negative value, which makes this negative sign on the v not only okay but important, because it's telling me that the delta x that I'm determining using the area under the curve is in the negative direction. It means I have changed my position in the negative direction. So the area under a v versus t curve is the displacement of the object. So again, more important information that we can pull out of one of these graphs to help us make these other representations. And so with that being said, I want to move on to the last representation of motion that I want to talk about at this time, and that would be the motion map. And so I want to describe that more clearly on the next page. And so when we do a motion map, essentially what we're doing is we're just looking for another way to look at the position change and the velocity change, potentially, of an object based on the space where it lives, sort of. And you've kind of already made these motion maps. And if I take a second to jump back to earlier, a motion map is a picture of where the object is at certain times. And so this right here is actually a motion map that we've made, right? And if you think about this, you've seen this because you could have looked at the floor while you were collecting your data and seen the paper clips laid out on the floor in front of you. And those paper clips were laid down on the floor every 2 seconds, every 3 seconds, every 4 seconds, whatever your group chose, but they were laid down at specific time intervals to mark the position of the object. And that's what a motion map is. And so what we're looking at here is most of a motion map. So let's go back to the other screen, and let's make a motion map for our object. And so what we're going to do is we're going to start with this number line, and my positive direction is over here, and my negative direction is over here. And so what we're going to do is we're going to say, okay, my object, being the object that makes this position versus time graph, has an initial position of some big positive value way up here. And so what I'm going to do is I'm going to put a dot right here, and I'm going to label that dot as t equals 0. So I know that that's where it starts. That dot is the dot that represents where my object was when my stopwatch read 0. And then what I'm going to do is I'm going to say, okay, every 1 second, say, or let's do 1 second. Every 1 second, I'm going to put a new dot on my motion map indicating where my object would be. And since I'm moving in the negative direction, I would say that if I am at this position at t equals 0, that at t equals 1, I might be at this position. Okay, that makes sense, right? So I'd be about right here, which is this position value. And then at t equals 2, maybe I'm at this position here. Okay, see, as I move down the axis, as I move along my graph here. And at t equals 3, maybe I'm at this position here. T equals 1, 2, 3. I'm just kind of moving along down my line. And at t equals 4, then maybe I'm at this position here. And so this is essentially a motion map. You can kind of think of it as a strobe picture where you're closing your eyes and then opening your eyes every second and seeing where the object is, and then closing them right away, and then opening it again. And the one thing that we're missing here is that I do want to be able to include velocity in this somehow. And so velocity is that vector that we talk about. And so we're going to include velocity, the velocity vector here, because we're going to use arrows to give us an idea of how fast this object is going. So what I'm going to do is I'm going to add an arrow right here from one dot to the next. And so the longer the arrow, the faster I'm going, and the arrow points in the direction that I'm moving. Now, all of my arrows in this case are exactly the same length, and that makes sense because I'm moving at a constant velocity. So my arrows, the velocity I have right here, and the velocity I have right here, and here, and here, and here, should all be exactly the same. And not only exactly the same, but they're also all moving in the same direction. So every arrow is pointing in the negative direction. And we've stated over and over in this particular situation that my object moves with a constant velocity, indicated by the same length arrows, in the negative direction. So my arrows are pointing in the negative direction as indicated by the fact that, hey look, this arrow is the negative direction. So the motion map, if we go back and add it to our nice concise 4-box screen, is something that should look like this. Let's see, we should put 0 position here. So essentially what I'm doing with this is I'm setting up my my coordinate system. I'm setting my reference point, my origin, and in this case I've started way out here at some big positive position, and I'm moving in the negative direction at a constant velocity. And you'll have to excuse that these may not be exactly the same length, but you get the idea that I keep putting dots, and the dots in this case represent every 1 second how far I've moved. So I've moved this far in 1 second, I've then moved this far in 1 second, and that far in the next second. And so here is t equals 0 because I started at some big positive position and I moved at a constant velocity in the negative direction as indicated by the length of the arrows and the directions that the arrows point. And so here what we have is we have a position versus time graph. The position versus time graph allowed us to write a written description, it allowed us to make a v versus t graph, and it allowed us to make a motion map. Now, in the future, what you're going to be asked to do is you're going to be given any one of these and be asked to make the other 3. So that's something that you need to be prepared for. Today we started here with a position versus time graph, and we wrote a description, made a v versus t, and made a motion map. In the future, perhaps you're given the motion map, and you need to write a description, make a position versus time graph, and make a velocity versus time graph. So given any one of these, you should be able to make the other 3. In addition to that, you should probably be able to also give the equation of motion or mathematically model what's happening, and that equation would look like something having the form of xf equals vt plus xi, since in this case for constant velocity these are all nice linear equations. Okay, and that pretty much wraps this up. The one last thing that I want to do is I would like to kind of summarize what's important and what we talked about today. So just to make sure that things are clear, we talked about x versus t graphs. And some important things about x versus t graphs are that the slope of an x versus t graph tells you the velocity, and that let's use the math class term, the y-intercept, okay, the math class y-intercept represents xi, the initial position. Okay, so those are parts of an x versus t graph that you can look at to help you get information. And we also need to remember that the slope of the velocity versus time graph tells you not only the value of the velocity, or at least qualitatively gives you a value of the velocity based on how steep it is, but it can also give you information about the direction that the object is moving. If the slope is negative, then you're moving in the negative direction. If the slope is positive, then you're moving in the positive direction. So the slope and the y-intercept, position intercept in physics class, give you good information about the motion of the object. Let's see, what else? Written descriptions. I'm just going to put WD for written description. Things to make sure that you do in a written description would be to talk about the initial position, where do you start, to talk about what direction you're moving in, and to also describe the velocity as best as you can based on the information. Sometimes you might be able to give an actual value if you're given data, or if there are numbers associated with your graph, if you know what the scale is. Other times it's just sufficient to say it's constant and in the negative direction. So that kind of depends on what you're starting with and what you're given. But written description should do this for all sections of a graph. Okay, all sections of a graph. Next we did the V versus T. V versus T graph. Important stuff from the V versus T graph for now, and we will talk about more later, is that V versus T graphs for constant velocity situations should be horizontal. Okay, because they are constant, they're not changing their value. And the other thing that's important is that the area under the curve will represent the displacement delta x. It will give you an idea of, during that specific time interval, how much you have changed your position. One of the things that we talked about in class is that if we don't know what the initial position is, then we can't actually draw the proper x versus t graph, because we don't know where it starts. But there are many correct position versus time graphs that we could draw, and they would all need to have the same slope. So a whole bunch of parallel lines with different starting positions would represent appropriate x versus t graphs when you're only given the v versus t graph. And finally, motion maps. Motion maps are important representations. We're going to use dots on a number line type setup, and attached to our dots are going to be arrows that represent our velocity. The length of the arrows are going to represent the size of the velocity, meaning sort of the magnitude. You can think of it as like the absolute value, how big it is. So an object with this arrow that's here, the orange one, versus an object whose motion map looks like this. The orange one is moving considerably slower, but in the same direction as the green one. So the length of the arrow is giving us an idea of how fast. So this says that 1 second later the green one would be here, and it would maintain the same velocity. And at the same time, the orange one 1 second later is right here. So you can see how one of these, specifically the green one, got out to a much better start and is moving much faster. So it moves farther in the first second than the orange one does. And then, of course, the arrow points in the direction that the object is moving. And finally, the last thing that I'd like to touch on here is the equations that we have been using and will continue to use moving forward. We know that the displacement, delta x, is equal to the final position minus the initial position. Displacement is a vector, so therefore it can be negative. You can change your position in the negative direction, so no problems there with that. We also found out that the average velocity equation is delta x, or the displacement, which again could be negative, divided by t. Average velocity is, if you have a constant velocity, this equation is appropriate to use for that, because your average would be equal to the actual velocity that's not changing. And then finally, if we need to mathematically model the motion of an object that's moving in a linear fashion with constant velocity, then we can use the equation xf equals v, the velocity, times time plus whatever the initial position was. And so, again, this equation rearranged actually is the definition and gets us back to that average velocity equation that's right above it. So these are the things that for now are important and that we talked about. Again, this was a recap of our constant velocity post-lab discussion.